Hi, this is Bert de Vries, and this is the Bayesian Machine Learning and Information Processing class. Today we're going to be talking about Bayesian machine learning, in particular the structure of Bayesian machine learning. Bayesian machine learning is another way of saying probabilistic machine learning. So we're going to lean heavily on probability theory. We've done probability theory in the previous lesson, and there were two main takeaways from that lesson. First is the interpretation of probabilities. We want to interpret probabilities as beliefs, as states of knowledge about a process rather than a real physical property of that process. Secondly is the calculus. The calculus is actually quite simple. Everything is based on the sum and product rule. There are two related rules that can be derived from the sum and product rules, namely Bayes' rule and marginalization. And we're going to use those two rules as well, but they can be derived from the sum and product rule, so they are not fundamentally new. Let's start with a very, say, basic machine learning problem, but it's also very representative for everything that happens in machine learning. I have a coin, and I throw that coin. It has, of course, heads and tails come up. Let's say what comes up is displayed here on the monitor: heads, tails, heads, heads, tails, tails, heads. And the question is, the challenge: what's the probability that heads comes up next? So the way this works, and it always works this way, is you first have to propose a model. Then we're going to use that model and the data that you observe here to basically fuse the information from the model with the information from the data. So we get an updated model. Now the model has absorbed the relevant knowledge from the data, and then we're going to use this trained model to make the prediction. And it's a very simple framework. And we're going to keep using this framework time and again throughout this class. So in short, here's the framework, the Bayesian machine learning framework. Suppose that you have an application to predict some future observation based on n past observations. I'm using here the prediction context, but this would just as well work for classification, regression, for any of the other problems. The Bayesian design approach involves 4 stages. First, you propose a model, the model specification stage. And we're going to go through this in a bit more detail after this slide. Secondly, this model may have parameters, and if so, you want to estimate these parameters from the data. So you have an observed data set, in this case something like heads, tails, tails, heads. You want to use that to update your model, so the model basically, you want to absorb the information from this data set. Third question is, now you have this updated model. How good is this model? Right? You want to have a good model before you make a prediction. So we want to evaluate this model, and we can now loop around until we get a model that we are satisfied with. Once we are there, we have a good model now. It has absorbed all the data. We want to use this model for our application, in this case prediction. And let's go through this in a bit more detail. It's specified, or it's laid out in the lecture notes, but just to slow things down a bit, I'm going to actually do it on an iPad, and I'm going to build the equations on an iPad. So the first stage is model specification. You have to design a model. And what is a model? Well, so model specification. A model is basically a probability distribution over all variables in your system. So you have observations, and the model has parameters, theta, and given the model, right? M is just the label of this model. Now, what you need to do is you want to actually specify these models in what's called a prior and a likelihood. The reason to do that is because it's usually the easiest way to specify a model. So this model can be specified if you would propose a distribution that we call the data generating distribution. Data generating distribution. And a prior distribution, parameter prior distribution. If you multiply the data generating distribution with the parameter prior distribution, you're going to get your model. So these two, this is your model specification, and you have to come up with proposals for that. That, by the way, is also almost your only task. From now on, everything is automated by the Bayesian framework. So if you have specified your data generating distribution, which is a distribution that says, I have a model, that model has given parameters. If I know the parameters and I know this model, I can actually predict the values for X. At least I can make the probabilities that it will land on heads or tails. This data generating distribution assumes that you know the parameters. What do you really know about the parameters? Well, you specify that in this distribution, in the prior distribution. So this was the model specification. 2 is parameter estimation. So we assumed we have a data set, right? X1 all the way through X capital N. And what I'm interested in is in computing the parameters for my model, given the data and given the model. Right? The posterior distribution for the parameters. What do I know about my parameters once I have specified my model and I've seen all the data? Basically, that's what this says. Well, we can use Bayes' rule for that, right? Bayes' rule says this breaks down in the distribution for the data given theta m times p theta m divided by p d m. That's Bayes' rule. Now let's look at these factors in this right hand side. This prior, you basically get that from here. You've specified that, right? So this guy you just put in there. This guy, the likelihood PD given theta given m. Well, if you make coin tosses, these coin tosses are independent, right? The outcome of the fourth coin toss doesn't depend on the outcome of the third or the outcome of the fifth. So in that case, the probability distribution for the whole data set is just the product of basically the probabilities of outcomes for each individual throw. And this guy here, well, you have specified your data generating distribution, so you can get that from here. So we can compute now the prior, because you basically gave it in your model specification. You can compute the likelihood function by taking this data generating distribution and plugging in all your values xn. So this now is also just a function of theta and m, and no longer of these values, because you can plug in these values. Let's look at the numerator, sorry, the denominator. The denominator, p of d given m. Well, this happens to be the same as p of d theta given m d theta, according to the rule of marginalization. And now I'm using the product rule again. This is p of d given theta m, p of theta m d theta, and this here is your numerator, right? What you see here is the same as what you see here. So we can compute basically Bayes' rule, because this guy, the prior, we got from our model specification. The likelihood we got from our model specification. We plug in all the data, and once we have the numerator, we can also compute the denominator by integrating out the parameters, by marginalization over the parameters. And basically that gives us the posterior distribution for the parameters. That's what we call parameter estimation. And crucially, I did not have to design some smart algorithm to do parameter estimation. Everything I did followed straight from probability theory. Probability theory will take care of how to do this. Once you have specified your model specification and you say, I want to compute now p of theta given the data, or p of whatever you want to compute given whatever you know, you can use sum and product rules to compute it. It's automatic. That's the beauty, or one of the beautiful things about Bayesian machine learning. So that's parameter estimation. Now, once you've done that, you want to know how good is the model. Model evaluation. How good is this model? Because you make these choices for a prior and for a data generating distribution, and how good were your choices? Well, basically, there's no point in coming up with a number here unless we have another number for another model, right? So we need to assume some alternative candidates. So let's assume we have some model set, M1, M2, all the way through M capital K. These are all alternative models, and I want to pick now one of these models. I want to find out which one of these models is the best model. Well, what I want to know, I'm going to state what I want to know always as a conditional probability distribution. I want to know what's the probability for model K given the data. That's what I want to know. All right. So what do we know? So our model specification stage, we have a data generating distribution for models K, and we do this of course for all K. We have a prior distribution for the parameters, and if we want to know a posterior for the models, we also need a prior. So we want to add now a prior for the models. Model prior. So that's what you need to specify. But once you have specified a prior for the models, a prior for the parameters, and how data is generated given your model and given your parameters, you can do everything again. You can basically compute the posterior for the models, basically the posterior for the models given the data. It's again just a matter of sum and product rules. Let's go do this. So we want to say P mk given D is what we want to compute. Well, that is P D mk times the prior for the model divided by PD. This is proportional to just the numerator. Note that I'm interested in the probability, I'm interested in the probabilities for mk. P of D is not a function of k, so that's just a scaling factor. That's going to be a constant, and we can always compute that by renormalization later on. What I'm interested in is the relative probabilities of the various mk's. Now this equals P d theta given mk d theta times P mk. That's just basically the reverse order of marginalization. When we do this, we did this before as well. We just added here in parameter estimation. We go from here to this formula. We added the parameters, sort of a reverse marginalization. That's called in statistics extending the conversation. You extend the conversation to include another set of variables. Here we do the same thing. I have P of D given mk, but I want to include my parameters. I extend the conversation, and now this is exactly the same, but now I have the parameters in there. I'm going to pull this P of mk to the front, equals P of mk times this integral. I'm going to just break that apart by basically the product rule. So I'm going to get P of D given theta mk, P of theta mk d theta. Now, this guy comes from your model specification. This guy comes from is the output of your, is basically also your model specification. And this guy is also your model specification. So now, where this guy, of course, we inject or we substitute all the values of the data because we want to take that along. But all three terms, all three factors, basically come from here. So you can compute this as well. And then you just look at the relative probabilities, and if you're satisfied with one of them, let's say you have a model with a very high probability and the other candidates have low probabilities, you say, okay, so that's my model, let's say the case one. Then you continue and you use that model for your application. And but crucially, if we compare models, we treat model comparison as a parameter estimation problem again. In this case, so M1, M2 through MK are now my different parameters or different models, and we compute posterior probabilities for these models given the data. It's the same recipe as for parameter estimation, now at one level higher in the hierarchy. So once we've done that and we're happy, then we can do the application. Now we want to use our model application. In this case, it's a prediction problem. But it could be a classification problem, it could be any other problem. Well, what do we do in prediction? Well, we want to compute the probability of the next point given the data. That's what we want to compute. Again, note that I write down my task as a conditional probability. I wrote down my task as a conditional probability when I did parameter estimation, when I did model comparison, and when I do my application. I write it down as a conditional probability distribution. And we can always compute that if we have the joint. And so when we have the joint, so this guy is simply P, of course this should be D comma M, but I've chosen my model. I'm going to leave that out the equation now. So this is simply then P xn plus 1. I'm going to take theta in there. Pxn plus 1 given theta times P of c given the data d theta. This is the parameter posterior. And this is basically your data generating distribution. So we can compute this. Your parameter posterior you got from your parameter estimation stage. This guy, the data generating distribution, you got from your model specification stage. So you're done, you can compute this. Well, that means if you can execute, or if this is a practical integral, and that's where Bayesian machine learning basically is complex. As you can see, we can always write down all the formulas, and we can if you will, conclude that machine learning is easy apart from computational details. I say that, of course, a bit tongue-in-cheek. Machine learning is not easy. The computational details are very difficult. It may be very difficult to compute this integral. It may be very difficult to compute this integral here. It may be difficult to compute this denominator here, because that's also an integral. So Bayesian machine learning often comes down to executing integrals, and they may be hard, but it's conceptually straightforward. You make some model assumptions, and from there on the game is pre-specified. You don't have to come up with a smart parameter estimation algorithm. You don't have to come up with a smart prediction algorithm. The probability theory will derive it for you. So that's the essential part here. And I'm going to stop it for now. I don't want to make this very long video. We're going to do an example for the coin toss in the next video. I'll see you there.